At night, like a night.
Yeah.
Ah!
You got it.
Nice.
Ah.
Let me move y'all over here so I can see y'all. Come on, change window size. There we go. Is that it? Oh, there's Amelia.
Now we just need Michaela.
Yeah, where is she?
I don't know. Do you want me to text her?
What are you doing?
All right. So we ended up with these examples as of last time, and I am recording. Okay, good. So here are some typos in this. So when we talk about the English system, so this was the metric, or metric system. In the English system, we'll talk about cubic feet, cubic yards, cubic inches. But with liquid measures, 1 gallon is 231 cubic inches. And this apparently, when I was cutting and pasting from HTML format, it did that weird stuff. Which is about 3.8 liters, and 1 quart is a fourth of a gallon, which is about 58 cubic inches. So if I wanted to convert 45 cubic yards into cubic feet, what do I need to do?
Would you have to multiply it by 3 2 times?
2 times or 3 times?
Don't confuse me. I don't know.
All right,
I
let's
should
look at
help.
that. So Sophie is hypothesizing that we multiply by 3 2 times. So the way
Well,
I
maybe,
so if I look at 45 and then
maybe
times,
it'd be 3 times, okay?
yeah,
Because 2 times would be squared, wouldn't it?
right. So that would be 45 times a yard times 1 yard times 1. 45, and then for every yard there is 3 feet times 3 feet times 3 feet, which is going to be 45 times 3 times 3 times 3 times feet times feet times feet, which is, what is that number? It's 9 times 45.
12:15. Or wait, no, I did that wrong.
Yeah, it is 12:15.
Yeah. Times 27, not 9.
Oh, yeah. See, Sophie, you messed me up.
I'm sorry.
There we go. 12:15. All right, see if y'all can do B and C for me.
I don't know if you're in a gallon.
Uh-oh. Y'all froze on me.
Well, I have an issue.
What's going on? Why are you frozen?
Are you listening to me or can you not
I
hear
hear
me?
you.
Okay, well, I don't know how many feet are in a gallon. Okay.
Y'all
I
are
see
all
that.
frozen. I hear y'all. I just don't see y'all.
I don't know if I know how to do B either.
Okay. Anybody
Just
else have
because
ideas on B?
Well, I was thinking it would be like 36 inches because that's how many inches are in a yard.
Right.
Is it 1 over 36?
It's way, way less than 36.
Okay.
Well,
So
like,
look at that.
I did 4,320 times 1 over 36 times 1 over 36 times 1 over 36. Is that wrong?
So so this would be 1 inch times 1 inch times 1 inch.
Yeah, that's about as far as I got.
Well, for every 36 inches, right? We know we have 1 foot.
Oh, 1 yard.
Oh, yes. There we go. So if I want to find 1 inch, if I divide each side by 36, 1 inch equals 1/36 of a yard. Like Ilsa said.
Okay.
Now these are yards. So it should be approximately 0.0926 yards.
That's what I got.
That's what I got.
Cool. What about C?
Well, first you have to change the 10 and then you multiply it by the 241 or whatever. Inches
231?
cubed. Whatever the thing was. I typed in my calculator. Actually, I can tell you.
231.
Yeah, it's 231. It is 231.
So I know 1 gallon equals 231 cubic inches, but I want to find cubic feet.
Well,
So if
first,
I had 10 of those, that would just mean
you start chugging around some zeros.
2,310.
now if I can change these cubic inches to feet, so this would be
But all you have to do is divide it by 12 3 times.
right, because then this would be times 1 inch times 1 inch times 1 inch, which this is going to be 2,310 and then 1/12 feet. Or divide by 12 3 times in a row, like Sophie said, right? And what do y'all get approximately there?
I got 1.3368.
36?
Yeah. Well, 1.336.
Oh, 336. There we go.
Or you can do 1.34 if you're feeling wild.
Yeah.
All right.
Feet, not inches.
Tony, you need to stop playing these games.
So that'll be approximately. Cool, right?
Yes.
All right. Okay, so now let's look at it comparing volumes of similar figures. So first off, are these figures similar?
Yes.
Why?
Because they're both like the first. To get the second one, all you have to do is divide all the numbers on the first one by 3.
Right. So the
The ratios are the same.
right. So this length is 6, and that length is 2. So if I take 6 and divide it by 3, I get 2. If I look at this length here, which technically you could view as the width, or the length with height. So this is the width, and I divide that by 3 like I did in this one, I should get 4. Check. And then the height, 6, if I divide that by 3, I still get 2. So these should be similar. Now, if I look at the volume of A, what is the volume of A?
$432.
Cubic units, right? And if I look at
Yes.
the volume of B, what do I get?
16 cubic units.
Yes. Now, if I look at the ratios of those volumes, I get 432 divided by 16. What is 432 divided by 16?
27. You know what that means.
Which is 3 cubed,
Yes.
which is what I multiply this by 3, or sorry, multiply this guy by 3, multiply that guy by 3, and multiply that guy by 3. That'll give me
Those guys.
the volume. So just like what we showed when we're talking about similar figures in the previous chapters, the scale factor for two similar figures being k, so the linear factors 6 and 2 have a scale factor of 3, 2 and 4 scale factor of 3, 6 and 2 scale factor of 3, and the ratios of their areas is k squared, then the ratio of their volumes is k cubed. Does that make sense?
Yes.
What's after, hold on, what's after 27? Like, okay, 3Q, okay.
Give myself some more room. There we go. All right. Now, we also have units of mass. And I'm pretty sure that y'all would have talked about this if you took chemistry or physics, you'll see these units come up to play. So mass is a quantity of matter as opposed to weight, which is an external force exerted by gravity. So when astronauts orbit Earth, their weights are going to change even though their masses remain the same. So mass represents a quantity of the matter, but the weight is how much force is exerted on you. And so when we talk about mass and weight, sometimes those are used interchangeably, which is technically not exactly correct, but that kind of like leads to the whole idea of that we use the term diameter to represent the length of the diameter of the circle, as opposed to the diameter is actually just the segment, not the length of that segment. So we have to be, that's one of those things that causes confusion later on when we were actually trying to differentiate the two. So when in the English system, weight is measured in this funky word. I don't know if anybody could pronounce that for me. And those are going to be tons, pounds, and ounces. And 1 pound is going to be 16 ounces, and that 12,000 pounds is 1 ton. But in the metric system, we'll have grams, which is what you primarily use in the science fields. And these work just exactly the same as the base 10 units. So if we look at these things in terms of volume, capacity, and mass, so if I had 1 cubic centimeter, which is equivalent to 1 milliliter of water, which would be equal to 1 gram. And then if we were talking about 1 cubic decimeter, which is 1 liter, which would equal 1 kilogram. So that's how they turn their base units. Then we also have temperature. Here we use Fahrenheit. Everywhere else uses Celsius. And these are the conversions here. So we can't just say for every degree temperature, we would just add 32. It doesn't work that way. And there's not this constant trend here of figuring this out, but there is a pattern, and it ends up being linear, where if I take the degrees Celsius to find that, if I take the Fahrenheit, subtract 32 from it, and then multiply it by 5/9, I'll get my degrees Celsius. If I know the degrees Celsius, I can put it into this form, which is the inverse function of that guy. If I had the degrees Celsius, multiply it by 9/5, then add 32, I get Fahrenheit.
Those are not inverses right now. They don't look like it. Because the 5/9 is going to be the distributive property, won't it?
So if I put in F for this, I should get C equals C, right? So
if this is on the test, will we get these equations?
you'll be given those formulas.
Okay.
So if I plug this in, order of operations, 32 minus 32 is 0. So I get C equals 5/9 times 9/5 C. C equals C. And do it.
The one uses a distributive property and the other one doesn't. That's my only issue.
Right. So like if we said that temperature, so like if this was our Y and this was our X, if I was to resolve for X as a function of Y, this is what you would get. So when you compose those two, you'll get an identity. That one thing equals itself all the time. Yeah, so when we do these on a test, but of course on the test, you will have your book. Because remember, everything is all take home now, right? But on the exam, if it was in class, I would have given you these formulas. So yeah. And I think if there was anything about unit conversions on the MTTC test, they would have given you like recall that this is the conversion rate. So
When is our test now?
Let me see. I know we were supposed to have one coming up soon.
Today.
Oh, oh, yeah, that didn't happen. Why is this not letting me open these? There we go. Oh, y'all are hiding everything. Okay, hold on. Math 104. Yeah, because we need 2 more tests, right? I just already had this open. So test 3. Yeah, because we're behind in our materials. Sort of, yeah. So we're going to finish 14.5 here. So I can actually write y'all's test on this. So it'll be tessellations. So the last section of 13.4 and then all of chapter 14. And I can post that by this weekend. And I'll give y'all about a week to get that done. Yeah. So it'll still happen this week. Just you will now have 7 days instead of an hour and 20 minutes to complete it.
Is it gonna be like we print it off and then just take pictures of it again?
Yeah, so exactly like what you would do with the quiz.
Okay.
So I can just write it all down because I don't have a printer.
Yes, that works too. No, Elsa, you're supposed to go out and buy a new printer just explicitly for this class.
Well, I actually have 2, but neither of them work, so.
You already need to buy a geometry tool set.
I know, the whole $7 for it. Yes, I know. Yeah, just make sure that if you are writing it like by hand, your answers, just make sure that you explicitly say problem 1. This is my work. So that way I've been having some problems in my other classes that they've been kind of not clear on what answer they or which question that they were answering. So we have to work on that. All right. Time is another unit of measure, but they didn't put this in the book, which I thought was weird, considering that this is one of the very common things that are or standards that are addressed in elementary school. So I figured that we would talk about time a little bit. I'm pretty sure all of us know how to read a clock, right? And if not, we can work on that. I've actually had students when I did interventioning, they're seniors in high school and still did not know how to read a clock. So it doesn't surprise me that you weren't ever taught that. So because I've seen it happen. So obviously time is just a element that's used to describe the progress of existence. There's usually an order to time, so that's where we get the past, present, and future. That also comes into play when we talk about literacy and understanding past tense, present tense, future tense. We're talking about when these actions take place. So that has a very important role in many other things in terms of understanding our language and order of things or sequence or history of things. So these are units of time, and technically 1 year is 365 days and a quarter of a day. So when we do every 4 years, those 4 quarters add up to 1, to where we get 366 days. And then these are other common terms: the century, centi, meaning 100, so that's 100 years. Milli, 1,000, so 1,000 years. So, yeah. So when we're looking at time, what time is it on the clock?
12:21.
Yes. What would it be in 7 hours and 57 minutes?
$8.19. So
Is that what everybody else got?
Yeah, that's what I got.
So how do we do that, Lauren?
it's basically like we're in base 60, right?
Yep.
Like from
So this part would be base 60, right?
yeah.
So if I added 57 to 21,
It'd
Shouldn't that be an
1
8?
hour and 19 minutes. And then you add the 7 to that and it'd be 8.
Yeah, that should be an 8. It should be
Yeah.
8:18.
yes, okay. So that would be an 8,
Oh, 18.
and then that'll be a 7. So that's 78. But I only have 60 minutes and an hour, so I'm going to take that and technically carry that over. So you could teach it like this. But since that's 60, base 60, like Lauren said, this would technically be an 18, and then I'm going to add 1, so that makes that 20. But I only use the numbers 1 through 12 because now the hours are base 12, right?
Mm-hmm.
So then this becomes, so 2018. So if I subtract 12 from that, that is 8:18. Now, could I use 2018? Do we have
Military
a system
time.
that allows for that?
Yeah, the military.
Military time. So this would actually, when y'all teach this, this could be something that y'all could talk about in terms of like a cultural context of what's actually happening here. Because in the military, they would say 2018, and they technically mean 8:18 p.m., right? Or if we were talking about this being AM, then it'd be 18 AM. So, but then this would be 0:21. So, does that make sense? And then, of course, talking about AM and PM is also one of those things that students tend to forget about. All right, so what happens if it was an hour and 20 minutes ago? What time would it have been?
11:01.
And then what about, what time will it be in 2 hours and 27 minutes?
2:48.
So what everybody else got?
Yes.
All right, what about this one? What time is it?
8:05.
What time will it be in 3 hours and 16 minutes from then?
11:21.
What time was it 7 hours and 13 minutes ago?
12:49. I think.
Yeah, that sounds right.
So if I subtract 13 from that 5,
Yes.
so that's gonna be 55 minus 2. 50. I have 52. Am I doing that right?
No. maybe. Hang on. Let me see. It's 805. If you subtract 13, then you'll get, yes, 52.
Oh,
That's 10. And then 3 more. 52, right?
Yes.
Yeah.
So that would make that 7:52. We're subtracting 30 minutes, so then it'd be 12:52.
Yes.
But now what happens if I move forward 7 hours and 19 minutes? What time is it?
12:24.
No. Wouldn't it be 3? Just not.
Because this was going back, right?
Oh, it'd be 3.
Yes, there we go.
If it's
324, I think.
it's 3.
324?
Yeah. I got
Yes.
324.
Yeah, 324.
Okay, cool. All right. Awesome. Now, there were things that students are going to get hung up on is that we said here, this is 12:21, but this is technically not pointed on the 12. Right?
You're not wrong.
Right. So one of those things that students get hung up on, let me see if I can pull this up and go directly to that link. And then I'm going to change my share to screen 1. Share. All right. And there's that website. So by showing these little, y'all see those little clocks?
Yeah.
Yeah.
Okay, good. I'm making sure that I'm not just talking about nonsense here to y'all.
No, there's a colored one and then a red one.
Yes. So when y'all see the hour hands that are in these little pie pieces, that would represent the hour, as opposed to seeing these kind of things. Like, this is fine. But then they see this, and a lot of students will say that this is 2:55 because it's pointing at the 2. And technically, it's about to be 2 o'clock, right? So it should be before. So this is slightly off the 2. So those are things that you want to watch out for when y'all are writing y'all's lessons on these or activities on these things. So like, and if y'all pick worksheets off the internet, I've seen ones that actually would say that this means 2:55 when it doesn't mean that. So you just got to be careful. So yeah, those are things that I just wanted to point out to y'all. So we go with that. Yay, okay. And now y'all have, let me close this and go change my share back to, go back over here. So now y'all see the notes again?
Yep.
Okay, cool. And then you'll have some homework problems there. All right, now we are into the last 2 and final chapters of the semester. Which kind of makes me sad that we're almost over. So this is how many pages long?
9 pages.
9 plus 18 pages left. That's it. That's it.
18 pages left for the whole semester?
No, that's not right. Oh, no, that is not right at all. I was about to get really upset. I was like, what am I going to do?
Well, I was gonna say we should probably just end class early if we only got 18 pages long.
So that was 9. That was 9. Plus 5. So that's 23. $30. 36. 43.
100 million.
43 plus 12 is 55. 59. Is that it? 55 pages left. Okay, I was going to say 18. That's not right. 55 pages. That's it. And chapter 10 will go really, really quick because it's mostly stuff that is just like facts, and we'll have some computational things to do in it, but we'll be talking more about like just the idea of data, and y'all will go more into the theory of it for those of y'all who are taking. I know some of y'all are taking 207 right now, right? Sydney, aren't you taking 207?
Is that stats?
Yeah, the stats.
Sorry, I'm making a sandwich, but yes, I'm taking 207.
Yeah, so I mean, the stuff that we'll be talking about in chapter 10 is going to be really similar to the stuff that, or the introductory part of 207. So, and I know some of y'all may have already taken it, so yeah, it'll be very basic stuff. All right, so probability. So in probability, we'll be using the set theory stuff. So that was chapter 2 of this book. So if you're having a very, very hard time not catching on based on our class discussions, please let me know. And I can get y'all more work on that part. But for the most part, I think y'all would be able to catch on just from the pictures that we draw. So here we're going to be talking about probability, talking about the difference between empirical and theoretical, talk about mutually versus non-mutually exclusive events. Then we'll talk about modeling probabilities with drawings, talk about the law of large numbers, and then talk about what an actual complement of an event would be. So we're not going to give it, like a compliment, or saying nice things about it. We'll be talking about what happens in the opposite of that event happening. So here's your standards. Probability shows up primarily in 2nd through 7th grade standards. So if we talk about probability, obviously we talk about probability in everyday life. So when you look at the weather and you see 20% chance of rain, that means on days that had similar weather conditions as the day has currently, 20% of the time it would rain. So that's how you would interpret it. Then you also talk about the likelihood of the Red Sox winning another World Series, chances of winning the Powerball, which are very, very minuscule. So yeah, those are things that we actually talk about in everyday life. The Common Core says that students should investigate chance processes and develop and evaluate probability models. Now, in terms of that, you can make the idea of changing things to probability by looking at them as opposed to just looking at these fractions and multiplying them together. If you put them in a contextualized or a concrete format, those things tend to make more sense to students. So looking at tree diagrams, or looking at spinners, looking at the actual cards in a deck, dice. Also, I've noticed that when we talk about these kind of games with cards and dice, a lot of students, even college students who've gone to college parties, don't know what kind of cards are in a standard deck of cards. So just letting you know, those are things that
They sound like they'd be fun to play poker with.
yeah. So just letting you know that those are going to be things if you decide to teach with decks of cards, that you actually review what is in a deck of cards. And then we'll also talk about counting techniques. So, which is something that we kind of talked about in 103, or we will be talking about in 103. So probability. So we have this dude named Pascal who had a friend who was a professional gambler, and he wanted just to know how to calculate their winnings or their chances of winning a game. So that's where we had the start of it. Then we also had Fermat. He came up with some problems, and that started developing the field of probability. And then Laplace, who is a very, very important mathematician, he also had probability theory applications. He's also really big in other fields of mathematics as well, and so was Fermat. So these guys were very, very important, and they made a lot of contributions to mathematics. But we don't need to know that, but just knowing the history and the context of it, these things. So technically, it looks like probability didn't come into play until in the 1600s. So fairly new in terms of mathematics. So when we look at probability, we're talking about a ratio. So that means we're talking about fractions that are less than 1, because you can't have something happen more than 100% of the time, right? Because either it happens or it doesn't. And so if it does happen, and we know it's guaranteed to happen, the probability would be 100%. But if it can't happen, like ever, it would happen 0% of the time, which means that probability cannot be less than 0. So if we get a negative number for probability, we have a problem. So those are things that you got to keep in mind. So
have a probability.
yeah. So if we look at an experiment, or looking at probabilities, if we have an experiment that is an activity whose results are outcomes of the experiment. So a simple example is that if we toss a coin, it cannot land on its edge, and we know that it's going to have either one of two outcomes, a heads or a tails, right? Assuming it's a fair coin, right? Okay. So if we look at all the possible outcomes for an experiment, it would be the sample space. Outcomes in the sample space cannot overlap. So that means that a heads and tails will not happen simultaneously on one coin. And then in a single coin toss, the sample space would be given. So it's a set S, and usually S represents sample space. And the elements that show up in that sample space for one coin toss would be either a heads or a tails. So if I wanted to describe the set size of that set, how many elements are in that set?
Are you still talking about the coin?
Yeah, the coin.
There's 2.
Two. So, and I know this will be coming up here later, but we could say that the size of S, or you could use this notation as the cardinality of S, would be 2. So like if y'all are Googling things or looking up things for lesson plan ideas, these notations tend to show up either this n of s as a function. So this means the number of items for this set S, or you can see these absolute value bars around them. That's just that is just the symbol for the cardinality of the set. And does everybody know what I mean by cardinality?
No.
I don't know what that word
The
means.
amount of things.
So by cardinality, my 103 student should know this.
I said the amount.
Yes, the amount.
Yeah.
Yeah. So cardinality is just a fancy word for size or the amount in that set. So like, for example, if we were to say we had the set 1, 2, 3, and we'll call him set A, we would say the cardinality of A, which is the same thing as the notation N of A, which is the same as the notation absolute value of A, which is going to be 3. Does that make sense to y'all? Cool. All right, if we look at the sample space of rolling a standard die, so that's this guy, the thing with all the dots on it, and the singular version is called a die. When we have more than one, we have dice. And his sample size or sample set would be the numbers 1, 2, 3, 4, 5, or 6, because those are the numbers that we have on our die. And because events are subsets of a sample space, so what do we mean by subset?
A set that has the same, some similar things of the set, but not all the same.
But can it have all the same?
Yes.
Yes. So for example, if we were talking about a subset of this sample space S, so using that idea, if S is the sample space, hold on, I think I get some water real quick. I'm dying.
Quick, everybody, leave the meeting. Okay, guys, this is where we tell her that it's 12:50, and that means it's time for us to be done.
Yeah, it's a short day today.
It's a short day.
Sorry, guys. I had that tiny tickle in the back of your throat. That when
Tony, it's 12:50.
it's a long day.
It's a short day today.
It's a short day.
I had to double check. If I didn't double check, I probably would have believed you.
Darn it.
All right. So, but that means tomorrow's the short day. So,
Why can't we have both?
because I want us to get through these things. We have all of those like 50 something pages to get through, right?
Yeah, and we have like 100 days left.
That's not true. We have like 16.
Yeah, that's still a lot of days.
I know.
I'm just saying.
All right.
Plus, we're not using up time to go over this by taking the test because we're taking it over the weekend.
How about the day that I make it due, we don't have class that day?
That's an interesting proposition. I can roll with that.
So I will let y'all know that, okay?
All right.
Okay. So, all right, so we have this as our sample space. So these are the only options that could happen when I roll a die, right? Now, if I consider this thing as the events where I roll only even numbers, that would be the numbers 2, 4, and 6, right? So this would make this a subset of the sample space. So we would say E is a subset of S. So that means subset. Which also can be written as E. So if you don't see it with the bar under it, that means this is a proper subset. These are interchangeable for E because E does not necessarily have to equal, but it could, just based on how we would define E. But in this case, E happens to be proper because he does not equal all of S. So that would make it a subset. So this would be an event. E is an event for sample space S. Just getting that lingo down. And yeah, and like I said here, if this still doesn't seem clear, I would skim through chapter 2. Or if you don't remember it, review it. So, but I think the gist of what we're doing here is probably all you would really need. We can also look at the sample space as a tree diagram. So if I draw this branches, so this is technically a type of a graph. That's a tree graph because it looks kind of like a tree, right? So if I was looking at my sample space being the flips of a penny, my outcomes are either a heads or a tails. If I look at rolling a die, my outcomes, so this would be my roll, my outcomes are 1, 2, 3, 4, 5, or 6. So it's a tree diagram. All right. Let's look at this problem. So suppose an experiment consists of drawing one slip of paper from a jar containing 12 slips of paper, each with a different month of the year written on it. Find each of the following. So what would be the sample space?
12.
Not 12.
Wait, not the
Would it
sample.
be 1 through 12?
So it has each month of the year written on each of the slips.
Oh, so it's January, February, March, April,
Right.
May, June,
There
July,
we go.
August, September.
So in my jar,
December.
I would have strips of paper that represent January, February, March, April, May, June, July, August, September, October, November, December. And we use the curly brackets to represent the set. Now it asks, find the event A consisting of the outcomes where the month begins with J. So there's my S, and I say A is the event where we only have months that begin with J. So who would be in there?
January, June, July,
Yes.
and August.
Nope.
Just kidding.
All right. B is the event where we have a month that has exactly 4 letters. Whose would those be?
June, July. I think that's it. It's hard when you didn't write out the full names for everything.
Sorry.
I'm just kidding.
Well, obviously,
You
I'm
don't
not
have to go back and write the full names. I was just kidding.
Well, if you were teaching this to elementary students, you would want to have the whole names written out.
All right.
So I was doing bad things here.
So why are we writing the names down instead of doing like 3 out of 12?
Because we want to write out the sets, not the probabilities yet.
Okay.
Because when we talk about the probabilities, the 3 out of 12 will come into play. And that's where we compare the size of the sample sets to, or sorry, the size of the event set to the sample set.
So you know to like write out the name when it has the event on it? Like when
Yeah,
it says
so in
event?
this case, we're actually looking at the way that this event would happen.
Okay.
And then when we look at the sides of those things, then that's where the 3 out of the 12 or the 2 out of the 12 will come from.
Okay. All right.
Because like if I was doing this in front of a class of say like 2nd graders, I would actually have like I would have my jar already in like with the slips of paper in there, and then I would start pulling them out and like showing them, so how many of these start with the letter J, and they would pull these out and that would be their set. So then when I go to this event that I'm only looking at the months that begin with the J, what are the chances that, or I shouldn't say chance, what is the probability that I would draw either January, June, or July from my jar of months? So they would already see that we only have these 3 chances out of all 12 possible outcomes. So that's where the 3 12ths would come from.
Okay.
And now if I was to look at this event C, where I'm talking about months that begin with M or an N. So not January, not February. March works. Not April. May works. June, no. July, no. August, no. September, no. October, no. November works. And then December, no. So now going to your question, how do we calculate probabilities? So if we consider flipping a fair-sided coin 10 times, would we always get exactly 5 heads and 5 tails?
No.
Or rolling a die 12 times, would we get each number exactly 2 times?
You could, but probably not.
Probably, well, I have a dice right here. So if I roll it 12 times, I got a 6. That's a not roll die. A 2. A 5. A 4.
I really hope you get each one twice.
That would be funny. a 2. A 4.
No.
You ruined it.
5. It's 1, 2, 3, 4, 5, 6, 7, 8. 4 more 9s.
That dice is loaded.
What?
Seriously, you haven't got any 1s or 3s. There's something wrong with it.
4 seems to be the majority there.
Oh, I rolled a different one and I got a 4. 3's there though.
Nope.
So no, it didn't work out that way. What about flipping a coin? Let me get a coin. Okay, so let's look at flipping coins. That's a heads, tail,
Heads. No.
tail,
I kind of hope it just somehow lands on its side and stays like that.
That's funny.
tail.
Hey, now you're doing this on purpose.
I'm flipping it, see? Tail,
Okay, that's not a flip. That was a chop.
tail,
This time make the head go right side up and not the tails go right side up.
still tail,
This time make the tail go right side up and not the head right side up.
ooh, it's spinning. It's still
Is
a
it staying
tail.
on its side? I didn't see that one. I don't believe it. You're just trying to prove a point.
Tails.
1, 2, 3, 4, 5, 6, 7, 8, 9.
What are the chances that you get tails 9 times in a row?
It was the tails again.
Okay,
It's a loaded coin.
But no, the head is there.
I don't see one.
It's right there.
That looks like a dummy.
And that was the tails.
I'm just kidding.
Does everybody else have a coin at
Why are
their...
you frozen?
I'm frozen. Oh no, y'all are frozen. Oh, there y'all
Bro,
are.
I'm so confused.
Are y'all there?
I'm here. I thought I was frozen, but then nobody
You
else
were
was.
frozen. Y'all weren't moving.
I was?
Yeah, all of you were frozen.
I thought you were frozen.
All right. Does everybody else have a coin at home?
I'm sure I
Yes.
can find one.
Here, I have a whole jar of them. Do you want me to
Those
let
of
you?
y'all who rolled or can do these, tell me how many heads and how many tails y'all get in 10 flips.
All right, I'm done. I got 5 and 5.
Nah, it's cheating. Actually do it.
I need space. Sorry, that's really loud, I think.
So I have 1 head, 9 tails. Are y'all there?
Uh-oh. We're joining the big screen, though.
I got kicked off. Hold on. I'm fixing it. There we go. See if I can see y'all all again. There we go. And somebody's checking. Okay, Hallie got 6 tails and 4 heads. Did anybody else get theirs?
I did. I got 3 tails and 7 heads. which is the opposite of what Katie got.
Oh, I didn't see what Katie got. I guess it got kicked me off when she typed it in. Alexis,
Well, here, do you want me to read them to you?
4 heads, 6 tails.
4 heads. 6
People
tails.
talking again because I think my audio bugged again.
Yeah, I'm talking.
Wait, what'd
Brittany
you
got
say?
4 heads, 6 tails. Katie got 3 heads, 7 tails. Haley got 6 tails, 4 heads. Sarah got 4 tails, 6 heads. Alexis got 6 tails, 4 heads. Kirby got 2 heads, 8
Oh, you're going
tails.
too fast. So I got Hallie with 6 tails, 4 heads. Sarah,
Yep.
4 tails, 6 heads.
Alexis got 6 tails, 6 tails, 4 heads. And Kirby got 2 heads and 8 tails.
All right. Let's see what we got here. So if we look at all the heads in total from everybody, I have 1 plus 2 plus 3 plus 1. Oh no, I counted that twice. Plus.
Hey, watch out because some of yours are reversed. Are you watching that?
Huh? Yeah, I'm watching that.
Okay. I was just letting you know.
So I have 1, 2, 3, 4, 5, 6, 7 here. So that's in 70 flips. So 1 plus 2 plus 3 plus 4 plus 7 plus 6 plus 4 is 27, which means the number of tails is 33. So is that really close to half of my heads and half of them being tails?
Pretty close.
That is pretty close, right?
Except for that only adds up to 60.
Oh, 70 minus 27. That's what it. 43. God damn it. You're right. That is not close to a half.
That is not close.
But definitely closer than what I had here, right? Only 10% of the time I would have got a heads, and 90% I got the tails, right? So with 70 trials, I ended up getting 27 divided by 70. Almost 40% of the time I got a heads, and then roughly 60% of the time I got a tails. So if I kept doing this over and over and over again, like thousands and thousands and thousands of times, these
They would converge.
they would converge to being half heads, half tails. So when I just do 1 or 2 trials, that's not enough to figure out what the probability is, but we can figure out what we can expect it to be. So that kind of gives us the idea of understanding the difference between experimental probability. So we did this experiment. So in these 70 trials, the probability of me getting a heads was roughly 38.6% of the time of getting a heads. So, but I know my real probability theoretically is going to give me 1/2, right? So with that, that kind of leads us into the idea of knowing that we need lots and lots of trials. So a real life example of this, I don't know if y'all are watching the news, but they were talking about the chloroquine treatment that of the people that they treated, 100% of them had positive results, but that was only like 100 people. They're talking about using chloroquine on the entire population to fight the coronavirus. Do you think only seeing what happens with 100 people is enough to say that it will work for the 7 billion people in the world?
No,
Well, in my
No.
not
stats
at all.
class,
No.
it said that you need at least 30 to make a standard group.
Well, it depends on what you would want to have for your efficacy of your trial. Because
30 out of like 100 out of 7 billion people, that's no.
no, you want to have large
Too
sample
little.
spaces to kind of see what the theoretical probable success rate would be. Because
So
here,
they're going to sample it on the whole population.
The bigger the
well,
group,
no,
the
they're
more
gonna do
accurate it's
trials.
going to be.
and there's going to be more controlled things that they can account for, because in real life experiments, there's a lot of variability. So that kind of leads to the whole idea of large numbers. So that's Bernoulli's theorem that says as the number of trials of an experiment increases, the experimental, or what's also called empirical, probability approaches or converges, like you said, Sophie, using the fancy number, will approach the theoretical probability. So when we talk about sample spaces, and like this is going to be something we'll talk about when we get to chapter 10 and talking about statistics, that if we look at a survey and they said in a survey, it was said that everybody loves the color green and thinks the color pink is stupid. So we can conclude that everybody says that green is cool, pink is stupid. But then you find out they only asked 5 people, when they were saying that represents like the entire university or the entire state of Michigan or the entire US population. Can 5 people actually represent the entire population?
And that's how I feel about the Electoral College. Thanks.
So those are things that you have to look at in order to understand the significance of those numbers that you're being told. So when we have lots and lots and lots of trials, looking at that, we can start to see that the experimental should trend towards the theoretical. So that's where they're coming out. And so here, when we look at probability, what we're going to look at, so going back to that question we had earlier, if I want to know what the probability of an event happening based on the size of the ways that these can happen, if I look at the number of elements of A and divide it by the total number of ways that it could, of an event could have possibly happened, that would give me the ratio of that number, or this would end up being a fraction that's going to be between 0 and 1, which a fraction can be converted to a percent as well, right? Or a decimal notation, right? So that's how we're going to view probability, as a ratio of the ways of the desired outcome divided by the total number of outcomes. So going back to that question where we're talking about, instead of saying writing out June and July, we would look at it as the probability of B would be the size of B divided by the size of our sample space, which gives us 2 out of 12. So that's where that is going to go. Okay. I think let's look at this picture and then we'll call it quits for the day. So we can also look at this being where every event has an equal opportunity of being successful. And if that's true, then we would have what's called a uniform sample space. In a uniform sample space, the n number of outcomes and the probability of each outcome is 1 over n. Here, this would not have a uniform outcome, right? Red is not as equally likely to happen as blue would, right? Because only 1/4 of the time red would happen. 3/4 of the time blue happens. So here is not uniform. Now, if it was split down the middle and this side was red, this side was blue, the event of blue happening is going to be equal as the event of red happening if they had the same area on that spinner. Does that make sense? So it's not uniform across. All right, so we will pick up with this example on tomorrow. I will work on getting a quiz for y'all on the chapter 14 stuff, and I will also put a test up there for y'all to work on over this weekend. And once I get the due date figured out, I'll have that for y'all as well. Yay? All right.
All right, thank you.
Have a
Thank you.
great day.
Yeah, y'all too. And I will
See you tomorrow, Joni.
I'll see y'all tomorrow. All right, bye guys.
Bye.
Bye.